All right, let's go ahead and get started. So I had an unusual start to my day where I couldn't make my office hours this morning, which I had some students who were coming in for help, and I wasn't able to help them. So I've decided to just do a slight extension on this take-home test. I know I had already extended it to today, but I'll say Friday, okay? Now that means you just have to get it to my inbox in my office by Friday. Let's say 2 o'clock Friday, okay? So if I'm not there, just go by, say I'm here, leave this for Mr. DiGiovanni, and they'll put it in the box. What I would do is ask them to like timestamp it, give you some evidence you dropped it off, because it has happened before where a test disappears. So, you know, cover your butt. You know what I'm saying? All right. So if you turn in already, you want to take it back and look at it some more, you can. It's up to you. All right. You want yours back, Hammer? Okay. Anyone else? Oh, you're welcome. All right. We need to finish up 11.3, which is actually what we were supposed to finish up today. So, like, we're going to get ahead today, which is not a bad thing. And I do have your new take-home. I'll give that to you in a little bit. So what we did not cover last time was implicit differentiation. Right? We talked about partial derivatives, right? If you have z is a function of x and y, or if we say f of xy, right? You have a function of two variables, then we can find this idea of this derivative, or we can compute this derivative by holding one of the variables constant, correct? All right, now to kind of get us motivated here, back in like Calculus 1 when we did implicit differentiation, we would have something like this. Sine, let's say xy equals x squared y squared plus 1. And you'd be asked in Cal 1 to find dy dx. Or they may have just said y prime, right? So in calculus, if we can get y by itself on one side of the equation, right, isolate the y, like if I can write y equals sine x, then we say y prime is cosine x, right? That's what we do. We just say derivative of the left side is y prime, derivative of the right side is cosine x. That's if we can solve for y. But in Cal 1, we realized there are some situations where it's impossible to solve for y. In other words, you cannot isolate y here in this equation. Cannot get it by itself. Or sometimes, even though we could, it's too much work, so we just do implicit differentiation anyway. So the implicit differentiation worked by taking the derivative on both sides of the equation, but you have to choose what variable you're differentiating with respect to. So in something like this, dy dx meant that we're going to treat x as our independent variable and y as our dependent variable. So y depends on x. X is kind of free, but x is not held constant, right? So what we did is we would have to apply any chain rule, product rule, power rule. We have to take all that into account when we do this. But we do derivative of this side, which would be chain rule, right? Cosine xy. Then chain rule says derivative of what's inside. What's inside there is a product rule, right? Between the x and the y, there's multiplication. So we have to do derivative of the x times the y plus the derivative of the y times the x, correct? So we would write derivative of x, which is, in this case, it's 1. Why is it 1? Well, the derivative of x with respect to x is 1. So we would get 1 there times y plus, now the derivative of y. So what's the derivative of y? Y prime. So depending on your instructor, they may have written y prime here, or they may have written dy dx. How many of them, if you remember this, wrote dy dx? Okay, that's the notation I'm going to use. When I teach Cal 1, I do y prime. But I'm going to do dy dx here because of where we're headed. All right, but it's important that you understand that that dy dx is actually the y prime. Okay, times the x, right? That's the full derivative over there on the left side. And then we have the right side, which again, we have product rule here. So the derivative of x squared is 2x, right? And then y squared plus the derivative of y squared. Now this was kind of a tricky part maybe when you were first learning it. The derivative of y squared would be what? Okay, good. First the 2y, that's your power rule, right? But then you go inside and take derivative of the base. The derivative of y was your dy dx. And then you have finish off the product rule, multiply that by x squared. That completes the product rule on the right side. Then the derivative of 1 is 0. And then after you do this, you would go through and you would say, okay, there's dy dx. That's what I'm trying to find in the problem, right? That's what I'm trying to get out of this. And then what we do is like distribute through and then isolate and bring the dy dx on one side, and we'd be done, right? All right, that's in Cal 1. So now in this Cal 3, we want to be able to do the same thing, but where we have an equation that has 3 variables instead of 2, right? We've got x, y, and z here. Well, when it was just x and y, we would say, okay, let's act like y is a function of x, so x is our independent variable. Or we could have in Cal 1 said, let's let y be independent and let x depend on it, on y, so we could have found dx dy instead of dy dx. But here, because we have 3 variables, we can't do a derivative. Just like when we had the function of 2 variables last class, we had to hold 1 variable constant, right? Same thing's going to happen here. If we are going to assume here that z, which we cannot solve for in this equation, if z is a function of x and y, and we want to know a derivative, we're going to have to hold one of them constant. So this is the notation for it. We want the partial derivative of z with respect to x. That means we will hold x as our variable, which means we have to treat y as the constant. Understand? This is different notation. This is, again, z is going to depend on x and y, but we're going to hold x constant and let y be our variable. And let's just see the difference between those 2 derivatives. Understand? You see the similarity here? See the connection? All right, so let's try this one. X cubed plus y cubed plus z cubed plus 6xyz equals 1. Does everyone understand that if you could solve for z, if you could, then z could be a function of x and y? And then we would do what we did last class. We did a couple of these, right? When I gave you that right there, right? I give you f of x, y is this, and then we could find partial derivatives pretty straightforward there. But now, in this problem, it's not easy to isolate the z. So since we can't isolate it, we use the implicit differentiation. Now, I like to do this whenever I'm going to do implicit differentiation. I don't know why. I've always just done that. I just draw like a squiggly line so everyone knows this means I'm going to do implicit, all right? So taking the derivative, right now, if I'm going to I'm trying to find partial z with respect to x. This means that what's held constant? Y held constant. Treating x as like the independent variable and z depends on it. So let's do it. What's the derivative of x cubed with respect to x? 3x squared. Okay, plus what's the derivative of y cubed? 0, because y is constant. So it doesn't matter what y is. Cube it, it's still a number. Derivative of a number is 0. Plus, Now, the derivative of z cubed. Z is not being held constant, right? Z is actually, we're treating it as a function of x, right? So we're going to have to use power rule first to get 3z squared. But then after the power rule, we go inside and we look at the base. We say, what's the derivative of z? We're going to say d partial, though. We won't say dz dx. We'll say partial z with respect to x. So times here partial z with respect to x. Do you see why the prime notation is not good here? What does the prime notation not tell you? This says the derivative of y, right? What does it not tell you? With respect to what, right? With respect to what variable are you talking about? You want it with respect to x, respect to z, right? I'll tell you a story. It's kind of funny. I think it's funny. You may think it's ridiculous. But when I was in graduate school, if you ever go to graduate school, if that's part of your plan, then pretty much the rest of your life is non-existent, right? So it's just eating and sleeping when you can and doing work, especially if you're like in a field like math or like physics or, you know, engineering. It's just, grad school's a lot. So I had this thing once a month, one Friday night a month, I would go out with my buddies and just let it all go, you know? Let all the stress go one night. And I liked to dance because, you know, you get that heart rate up and, you know, sweating out there on the dance floor type thing. That's what I enjoy doing once a month, right? So being out there in the social, you know, whatever, right? You're out there socializing with people. I would meet members of the opposite sex, obviously, and I didn't have any time for anybody, right? I mean, it was pretty, you know, what do I have to offer you? Nothing. You know, I'm going to be locked in a cubbyhole doing math for the next, you know, 28, 29 days, and then I'll be back, you know. So I usually didn't want to, you know, get into small talk and stuff like that, you know. It was just like, so I always had like a minimum bar question that I would ask a girl if they wanted to engage in conversation. And my question is, it's pretty, I think you might find easy. It was what's the derivative of x? And I mean, that's a minimum bar, right? I mean, that's like some Cal 1 knowledge maybe, right? So I'm out this one night and I meet this girl and we're dancing, we're having a good time. And we go to the bar and it's the end of the night and she wants to get my number and I just ask her straight up, you know, what's the derivative of x? And her response is, with respect to what variable? And I went, whoa. Okay, so I was like, all right, maybe we can talk. So then I said, if you take all the numbers in the interval 0, 1, and you close your eyes and randomly pick a number, what's the probability that it's a rational number? And she said 0, and I was like, whoa. You know, so I was like totally blown away. Anyway, we exchanged numbers. She lived in Wisconsin, and we are still friends. We don't talk very often, but we're still friends. She programs the robots that build cars. So like she'll go to like a Toyota plant, and she programs the computers so that they do all that stuff. Anyway, very bright girl. What's that? The welding stuff, they use robots that do the what? The welding. Welding, yeah, exactly. So it might be the welding robots. I'm not sure what exactly. But she was a smart girl. So every time I get to this thing where I think about this, I think about her. Y prime is not enough. That's why that notation is not that great. It's okay in Cal 1, but it's not okay here. So we need to know the variable that is dependent, right? The z is dependent on the x, and then everything else I'm treating like a constant. All right. sorry to share that with y'all, but all right. So where are we here? Now we're done, and we move to this. Whoa, what do we have here? It's like a triple product almost. But really, there are only two variables in there, right? Z depends on x. X is our independent variable. Y is a constant. So I could just split this right there and do a product rule here and here, right? So what's the derivative of 6xy with respect to x? 6y, right? This y is a constant. So we'll have just 6y. Now, with the product rule, I have to tack the z on there, right? Then I say plus the derivative of z with respect to x will be partial z respect to x, yes? And then 6xy. I had to give you that little background story about grad school, because if I tell you that I used to go out and I would ask girls what's the derivative of x, that just sounds really stupid. But I mean, it's just, I mean, really, I mean, if you go to grad school, you'll see, I mean, you just don't have time for it. So you have to find someone who's at least willing to listen to the crap you're going to talk to them about if they are, you know, I mean, if you want to talk, I'm going to be talking math, so hopefully we can chat a little bit. Okay, equals what? Am I done up there? 0. And so in here, you've got your partial z with respect to x. It appears in 2 places. So you move things around algebraically to the other side of the equation, you isolate it, and you're done. Okay? I'm not going to work through the rest. But any questions on that? Now I can also do the next thing that's being asked, which is partial z with respect to y. This time I'm going to hold what? X constant. This will be very similar, except x is going to be constant. And let's just work through this kind of quickly and see what we get. Derivative of x cubed would be 0, right? Derivative of y cubed would be, so this means x is constant, right? This would be 3y squared. Chain rule. Do we have to worry about the inside? What's the derivative of y with respect to y? dy dy, basically, so it's 1. So you don't have to have that there, right? But please understand that the reason it's a 1 is the same reason that the derivative of x cubed was 3x squared when it was with respect to x. Go follow? Okay, plus what? Derivative of z cubed, 3z squared times, now the derivative of z, but that does matter now, right? So z depends on y, so it's partial z with respect to y. Done with that, move on. I still have a product rule here, don't I? I can actually leave that line there, can't I? And treat x like my constant. So what's the derivative of 6xy with respect to y? 6x, and then the z from the product rule, plus the derivative of z with respect to y, right? Partial z with respect to y times 6xy. That's product rule, finishing it off, and then equals 0. Very similar results, right? Very similar results. That's only because the equation kind of looked the same. Now, we're not going to do this, but would it make sense for me to ask you, or could somebody ask you in this problem what the partial of x with respect to z is? Could they do that? Sure. You would act here, you would treat z as your independent variable, you'd say x depends on it, and you treat y as a constant. And you go through the same process. What other things could we ask? Partial x with respect to y, right? You could do partial y with respect to z, right? Partial y with respect to x. So there's several possibilities here, right? The ones that we're most interested in right now are these two, because we've been trying to treat z like it's a function of x and y. We have not been trying to treat x like it's a function of y and z. But you could. You could. You have to remember in the big picture of things what this is giving you. When you say right here, partial of z with respect to x, you're saying, I have an equation, right? Z is changing. As X and Y changes, Z changes, right? That's what this one right here is. You change X and Y, Z changes. If you hold Y constant and just change X, this gives you the instantaneous rate of change in Z with respect to that change in X. So you're basically saying, how much does Z change as I change X, holding Y by itself? Or down here, it's saying, okay, look, hold Z constant, hold Y constant, change your Z a little bit, and tell me how much X changes by. In the infinitesimal, right? The partial derivative means infinitesimal change. So if this equation, if the X, Y, and Z here represent, I don't know, pressure. I'm just trying to think of some equations that have multiple variables. What's this equation? P V equals nRT. Have you all seen that one before? Pressure times volume equals number of moles. That's a constant, and then temperature, right? So basically, these two are usually known, right? You know your number of moles and you know your Avogadro's constant. Is that what that is? No, it's not Avogadro. It's something else. Chemistry was like 20 years ago. Yeah, there's some constant there. But there's three real variables, right? And since there's three variables, I could say, hey, look, I want to know how the pressure is going to change if I just make small changes in temperature, which means I need to hold the volume constant. So I could ask for partial P with respect to T, right? But there's nothing that stops me from saying, hey, well, how does the temperature change if I hold pressure constant and let the volume of the container change? So all of these partial derivatives make sense. Y'all seeing the connection here? We stick with X and Y, partial with respect to X, partial with respect to Y, because of the geometric situation we're in Cal 3. X and Y are usually the ground, and then the Z is the surface up there. All right, I hope that makes sense. I'm not trying to make this hopefully useful at some point later down the road for you. All right, that's it for 11.3. 11.4 is next. 11.4 is a pretty short section. Tangent planes. The tangent plane to a surface. If Z is a function of X and Y, so Z is a surface, and F has continuous partial derivatives, that means you can take the partial derivatives, and those partial derivatives are nice. They behave well. Then the equation of the plane, which is tangent to the surface at a particular point on the surface, is given by this equation right here. And then I put here, so the normal vector of the tangent plane is this. So let me bring something up here. I hope you remember this. This is the standard equation of a plane, isn't it? That's your standard equation of a plane. X naught, Y naught, Z naught was any point on the plane, right? And ABC was made up the components of our normal vector, didn't it? And that's all we ever needed to define a plane, a point and a normal vector. Once we had that, we could define the plane. Because remember, the normal was perpendicular to the plane. Well, look back at this formula, and let's see if this makes sense. Partial of F with respect to X is our A. Partial of F with respect to Y is our B. and our z is -1. Okay, so do you remember last class I was trying to give you the idea of the partial derivative? We said we stepped out so many from the wall and then came over, and then I'm standing on that point. The partial with respect to x, I'm going to just stand here instead. So let's say I'm at some point. The partial with respect to x gave me what? What did that represent? Slope holding with respect to x, so holding y constant, which would be this way, wouldn't it? So if I'm standing here, then basically there's a curve coming this way, like this. The partial with respect to x would be the slope of a tangent line here, wouldn't it? So imagine a tangent line like this. I've got a slope of it. Now, what's the partial with respect to y standing at the same point? Another slope, right? A different slope, but it's when we cut it this way, we have another curve coming like that, and that would give us that slope. And if I look at this slope right here as a vector, I look at this one as a vector, and then just take our z component to be straight up or straight down, right? Does that make kind of sense? This direction, and then just a straight up and down z should represent our normal vector off that plane. So I'm just trying to get you to see where it comes from. I'll show you a better picture. How about this? If we had a sphere, right, a ball, and you were at the North Pole, right, what's your normal vector? It would be, your plane would be flat, right? If you imagine a tangent plane to the sphere, then your normal vector should be pointing straight up, correct? Do you all see that? So you would just, or you could say straight down. It doesn't matter, remember, with the normal. Does that make sense? So if I'm at the top of the ball, if I come in partial with respect to x, it'll look like a circle, won't it? What's the derivative at the top of that ball? Right, at the top of that circle, what's the derivative there? 0, right? So that would mean this is 0. And then if I come in this way, same thing, right? The derivative there would be 0, so that would be 0. And then this would always be -1. So that would give you the vector 0, 0, -1, which would be pointing straight down. I hope that makes sense. We'll see more visuals, but I'm just trying to get you to convince you that it makes sense that our normal vector would come from those two partials, or at least the x and y components of the normal vector would come from that. So this is just a formula, all right? If you like formulas, it's just something you need to remember. So let's take a look at this surface, and let's find the equation of the tangent plane. And I think what I'll do is first let's look at it, okay? So here is our speckled surface, right? And I have some arbitrary point here. We are supposed to be looking at the tangent plane when at the point 1, 2, 1. That means when x is 1, y is 2, and z is 1. If I go to that point on the plane, on the surface, I want to imagine a tangent plane. Tangent plane is kind of like a tangent line. It passes through that point, but is tangent to the surface. So let me, I'll just show you the tangent plane. Here's our tangent plane right now. Does that make sense that it would look like that? At that point right there, it looks like we're kind of at this, we call this a saddle, because it looks kind of like a saddle. In one direction it goes down, the other direction it comes up. Does it make sense to you that the tangent there would be almost like just the xy plane? At that point only, yes. Yeah. On a sphere, it's easier to see because the idea of a tangent line came from the circle, didn't it? So like when we go back and we look at, you have a circle, tangent line. The definition of the tangent line on a circle was basically that it was orthogonal to the radius going out to that point. That would be orthogonal, but you would also say that that line only intersects that circle in one point, right? That line. But then in Cal 1, we had to find out what did we mean by the tangent line to this curve at this point. Or you know what? Not that point. Let's say this point. We all agree that geometrically the tangent line would look like this. Does it intersect the curve at a single point? There, yes, but doesn't it come over here and intersect? But locally, in that little region, it intersects at one point. And it kind of like, it doesn't balance on the curve, but I don't know, have we all just accepted that that geometric picture makes sense as tangent line? We don't have a radius coming out because it's not a circle. So you can't use the same definition. Yeah? But in our picture here, it's that same principle that that tangent plane is going through that point, but it's like the best tangent plane we can get. If I move this thing around, I can move it by dragging the point over here in the domain. You can see how the tangent plane changes. So now I've moved, y'all see where I am on the surface there? You can see the tangent plane moving with me. I want to know if I go exactly to the point 1, 2, x coordinate 1, y coordinate 2, the z coordinate will be 1 when you do that, when you plug in the x and y. Plug in this for x, 1, and plug in 2 for y. Plug it in to the function, you'll get 1 out. So at that point, what's the equation of that plane? All right? So we have the function 1/2 xy. We want the equation tangent plane at the point 1, 2, 1. Is everyone clear that where 1 comes from right here? This 1 right here? You just plug in 1 for x, 2 for y, you get 1 out, right? So this is like the z value, x, y, z. Now, the formula that we're going to use is the one I just showed you, this one right here. So we're going to need to take the partial with respect to x, right? And then plug in x naught, y naught. And then take the partial with respect to y, plug in x naught, y naught, and then that'll always be -1. That'll give us our normal vector, and then we just plug in x naught, y naught, z naught right in. Ooh, yeah, y naught right there, and z naught right here, and we have the equation. So if you want to, you could label these x naught, y naught, z naught. Well, let's get our partials. What's the partial f with respect to x? So I'm just doing a partial right now. I'm not plugging anything in yet. With respect to x, what is it? 1/2 y. Partial of f with respect to y is 1/2 x. Now, what's the partial of f with respect to x at the point 1, 2? So you're taking this equation here and you're replacing this y right here with 2. So you just get 1, right? Over here, you're replacing x with 1, y with 2, but there's only an x in there, so we get 1/2. Okay with that? So I'm ready to write the equation of the plane. It should be partial of f with respect to x at that point, which is 1, times x minus x naught, which is 1, plus the partial of f with respect to y at this point, which is 1/2, and then y minus y naught, which is y minus 2, then always -1, and then z minus z naught, so z minus 1 equals 0. And then you could clean it up, but that's the equation of the plane right there. The equation of the tangent plane at that point. Questions? So, I mean, this is actually pretty nice because, you know, given any surface, as long as it can be written as a function of x and y, and as long as you can take the derivative and it's a nice derivative, then you should always be able to give me a tangent plane anywhere on that surface. Yes. It was given, and it has to be given if you want to know the exact tangent plane. If If you wanted a general formula for the tangent plane, then you would have to leave the x naught, y naught, z naught unknown here. You could find the partial still, but without the actual x, y, and z value, you can't get the specific plane we're talking about. All right, so there's our picture. Find the equation of the plane which is tangent to arctan xy squared. That'll be your in-class quiz. Let's do it. It'll help get your blood flowing a little bit. All right, so let's. You want to work through it or not? Yeah. Yes and no. All right, so I'll do it. So our function was arctan x y squared. I'm going to write it a different way. Arctan xy squared. And we want to be looking for the equation of the tangent plane at the point 1, 1 pi over 4. Yes? All right, so first thing I need is the partials, right? So let me go get those. The partial of f with respect to x. I'm not going to write x, y in parentheses there. I'm just going to do that. We said it was 1 over 1 plus whatever was in there, so xy squared, but squared. So x squared y to the 4th times the derivative of what's in here, which is a product rule, right? So product rule on that, I'm treating y as my constant and x as my variable. Oh, so I don't need product rule, do I? Or do I? Do I have to or do I not? Is that where you were hung up on? It should get the same answer either way, all right? But you'd have to be careful. So let me do it the way that would be easier, which would be, look, if y is constant, right? If y is constant, then this is just like 4x, and derivative of 4x is 4. So you should just get y squared, and that's it. But if you had done that as a product rule, then you would say, what's the derivative of x with respect to x, which would have been 1 times product rule y squared plus the derivative of y squared with respect to x, treating y as a constant, which would mean it's 0, right? You would have had 0 here times x, and that's still y squared. So you should have got the same thing either way. Now, what's the partial of f with respect to y? Same thing here, right? Now I'm treating x like a constant. So what's derivative of y squared? 2y, and that's it, right? 2y times x. 2xy? Okay. Now let's go ahead and figure out what the derivative with respect to x is at the point 1, 1, right? Because I gave you what x naught and y naught were here. At 1, 1, plug on it in there, and what do you get? 1 over, that's 1, so 1/2 times 1 squared, so it's just 1/2. The partial of f with respect to y at the point 1, 1 is what? 1, right? So it's 1/2 times 2, which is going to be 1. And that's all we need, right? So we have 1/2 x minus x naught plus 1 times y minus y naught minus 1, it's always minus 1, z minus z naught, which was pi over 4. equals 0. Y'all agree? That's it. All right. So homework-wise for this section, let me just correct the page number here. Is there not homework for that? Oh, yeah. Oh, this is the equation. This is actually it right here. This is what the surface looked like, and that's the plane that we found right there. This is page 648. Problems 1 through 6. All those problems are just find the equation of tangent plane. Now, it's something I'll mention here that's going to come up later is that right now we have a very powerful way of finding the equation of a tangent plane, right? Very powerful way. But what we're relying on is that we're looking at a surface that can be looked at as a function of two variables. So it has to be able to be written z is equal to f of xy. Understand? So if someone gave you right now an ellipsoid, three-dimensional egg basically, you could not use this equation or this formula for that because the ellipsoid is not a function of x and y, is it? Remember, an ellipsoid is a quadratic surface, and so it has an equation that represents the surface. You would have to be able to convert that equation into z equals f of xy for you to be able to do that. So you actually could get around that by doing like the top part of the ellipsoid and the bottom part, but you couldn't. We don't have a formula that handles all the quadratic surfaces yet. There's one coming, but when I get to it, let's make sure we distinguish it between this one. This one only, you can only handle surfaces that are functions of x and y. Later on, even a more general formula. Okay, I don't have notes for 11.5. I mean, yeah, 11.5, because they're too hard to type up because of everything I need to show you. So instead, I'm just going to write the notes down. Y'all just going to need to kind of copy me and get the idea, all right? So there are no 11.5 notes that I provide. So 11.5, it's called the chain rule. Did anyone print out Chapter 11 notes? There's an 11.5, right? There is. But it's, why wouldn't it come up there? Oh, because it's a PowerPoint. That's why. It didn't come up. Let me see if I can find it real quick. I forgot that I did put that PowerPoint out there for y'all. No. Well, it doesn't matter. I'll go through them, but I'm gonna write down a lot of this stuff on the board on here anyway. So if you don't have them, no worries. All right, let's just think back to Cal 1 when you were asked to find something like, or you were given something like this, sine x squared, and you were asked to find y prime, which we don't like that notation, dy dx, right? Then you were taught like, okay, well, chain rule, you start with like the outer function, you take derivative of that first, right? Which here would be the sine x is the outer function. The derivative of that is cosine. So you write cosine with the x in there still, and then multiply times the derivative of what's inside, right? Well, we could, if we wanted to, all right, we could have said that y is sine of, let's say, u, and u is x squared, right? And then in order to find the derivative, you could make a table. Now, look, I understand everyone here knows how to take derivative of sine x squared. That's not the point. Just let's try and get into like the method of what we were doing, and then we're going to translate that into like what we're going to do when we have more than one variable in there. So if I do that, I can write y is sine of something, right? That something is x squared. And then next to this, I can write the derivative. The derivative of y would be cosine u. And so really that derivative of y really means dy d what? U here, right? Because u is our independent variable. So I'm saying that the derivative of y with respect to u is cosine u. And then here I would say what? The derivative of u with respect to x is 2x. Did y'all see that? U depends on x, y depends on u. So derivative of y with respect to u is cosine u. Derivative of u with respect to x is 2x. And then our answer is just this column multiplied, isn't it? Our answer, dy dx, is just equal to that dy du times the du dx. And do you see how the Leibniz notation makes sense here? Dy dx should be these two multiplied because it's almost like the du's go away and you have dy dx. What was dy du though for us? It was cosine u times, and then what was du dx? 2x, but then what was u? I'm trying to replace this u right here. What's that u? It's x squared, so that's cosine x squared times 2x, which is exactly what you would have done had I just started with that and said, what's the derivative, right? We don't go through all this method of getting a table, and it's kind of a waste of time. All right. The moral of the story here is that if y depends on x, right, you could somehow break it down where y might depend on some other variable like u, and then that might depend on something else, and then you can use this Leibniz notation to kind of write out what the chain rule is. Yes? Also, the other moral of the story is that if you look at this problem right now, we would say that y depends on x, right? That's the way I'm going to write it, vertically. The y, in order to know what y is, I need to know what x is. So there is a direct connection between y and x, isn't there? A direct link. And so when I talk about taking derivatives, it makes sense for us to ask, what's dy dx? What's the derivative between these two? How is y changing with respect to x? Makes perfect sense because y depends exactly on x. All right. Moving along. If I put something like this now, z is equal to x sine y. What is it that I could ask for here? What is it possible, like derivative-wise, what could I ask for? I could do, but it would have to be partial though, wouldn't it? Correct? Those two would make sense to us? I mean, geometrically, this is a surface, right? And these partials are those slopes of those tangent lines, right? But I can only ask for one or the other. I can't ask for them both at the same time, right? I have to hold one variable constant, leave the other one free. So what I'd like for us to see here is what we're going to call a tree diagram. It's a way of getting our heads around what derivatives are possible and how we would actually compute them as these things get more and more complicated. So I'm going to start off with the variable that is dependent. The z here depends on x and y, doesn't it? Z depends on two different things. It depends on x and it depends on y. If I give you just x and ask you to tell me what z is, you can't, right? I have to give you x and y. So x and y feed to z. That's our tree diagram. Now, since z is at the top of our tree, that's the thing we're going to be wanting to know the derivative of. The derivative of z. It's just the question now with respect to what variable. Well, we have two possible variables, right? In the previous picture, y was at the top of our tree. The only thing that was possible for us to talk about was the derivative of y with respect to x. Yes? Yeah? Yeah? Okay. Now, since z comes down to x and to y, I can come down this branch of the tree and I can talk about the derivative of z, but because z depends on these two things, I can't say the straight regular derivative. I can say the partial of z with respect to x, or I could say the partial of z with respect to y. There are two possible derivatives for this scenario. You can get that one or that one. See that? Yes? Now, I'm not going to ask us to compute them, but just to see what's possible here as far as derivatives. Here's another example. What if I tell you that z is x sine y, and, so comma is going to be and, x is equal to natural log t squared, and y is equal to e to the t. So z, in the first equation, z appears to depend on x and y, doesn't it? So I could start out a tree like this. Z is at the top, z depends on x, and z depends on y. However, the next two pieces of information tell me that the x depends on what? T. So there's a straight line connecting x down to t, right? And x down, or y also comes to t. Now, I've seen sometimes where we put these together into one t, but I would caution against that. If they both depend on t, just make them go to their same t, or to different t's. So ultimately, z depends on one thing, right? You give me t, I give you z, right? All I need is t to provide you what z is. Now, because of that, there is only one derivative possible for me to ask, and that is, what's the derivative of z with respect to t? That's the only thing possible. If I want to go from the top of the tree to the bottom of the tree, that's the only thing possible. But my question to you, is it this or this? Well, and before you answer, for this problem, the only two possible derivatives that I could ask you for are these two, right? Because there were two branches. So those are the only things possible. But also, z depended on two different things, not one thing. So you come over here, the partial is reserved. Well, you answer the question. What do y'all think? What does your gut tell you? The straight derivative or the partial? Straight? Okay, and it's basically because you can get z straight from t. Think of it that way. And then the partial is Well, if you can't get z without knowing more than one thing, then you're going to use partials. Okay, so this is the only one that I could ask you on a test here. I could not ask you for that. It wouldn't make any sense. Okay? My question to you is, what is it? What's the formula for it? Like, how do you find the partial of z with respect to t if you've got all that up there? So there's an easy way to do it. Now, you could, right now, you could say, let me replace this x right here with natural log t squared, right? You could say, let me replace y with e to the t, and then you could go through all the differentiation, couldn't you? But the chain rule is supposed to make it easier. And here's how it'll work. Let's draw our tree diagram going down each branch and talking about the derivative off each branch. What is the derivative of z with respect to x? Right here, where my arrow is, I need to put a derivative down that branch. Is it going to be a straight one or a partial? Partial, because that's where my z depends on two things here, right? So I will put there partial z with respect to x, right? Right here, got that? And then from x straight down to t, that's straight derivative, right? X depends on t. So from here to here is dx dt. Over here on this side, partial z with respect to y, and then straight down, dy dt. Regular derivative. Now, we should only get one answer, right? There's only one derivative possible. We already said that. So how is it connected to this? What do you think it is? And I'll go back here again and remind you what happened here. When we wanted straight down, right, all we did was multiply those together. So when we're going down branches of the tree, we multiply what's there. So this right here should be equal to the product down the first branch. So partial z with respect to x times dx dt. What do you think I do with the other branch? Does this come into play? Is that part of this answer? It has to be, because there's only one derivative possible, so you have to count for this branch also. I know it's going to be this times this, but how do I combine it with this? What do you think? Add. That's exactly right. You do products down the branches and you add the branches together. So if I add to this the partial of z with respect to y times dy dx, dy dt, that is dz dt. It's this, and you have to figure out what that is. So can we do this? I'm going to do it down here. I'm bringing this here. For this specific problem, what is the partial of z with respect to x? So go up here. With respect to x, it's just sine y times what is dx dt? You take derivative of this, right? Pop the 2 out first, right? Can't you pop a 2 out since it's a log of something squared? The property of logs, that powers come out. So what's derivative of 2 natural log t? 2 over t. Now plus, what's partial of z with respect to y? X cosine y times the partial of y with respect to t, which is e to the t. And that's it. That's your derivative of z with respect to t. Now, your answer here should have just t's in it. Right now it has t's and x's and y's. So how would I get rid of that y right there? Yeah, what's y? You go back up there, what's y? It's e to the t, isn't it? And then right here, you'd replace x with natural log t squared, or 2 natural log t. Replace that y with e to the t. And then you would have a nice representation of the derivative of z with respect to t. I won't do it, but y'all understand what you'd have to do? All right, let's try something else. What if I say z is equal to x sine y? What if I say x is equal to r plus s squared, y is equal to r times s squared? If z is at the top of our tree, what does z depend on? X and y, right? But what does x depend on? R and s. What does y depend on? R and s. So z depends on two things, x and y, but each of those depend on two things, r and s. R and s. So can you get z by just knowing one thing? No. In order to have z, you're going to have to know two things. Ultimately, you're going to need to know what r is and what s is, right? And if that's the case, then what derivative is possible? Only partials, right? And what partials are possible? Z with respect to r or z with respect to s. Those are the only two possible derivatives in this scenario because z depends on more than one thing. The only partials that are possible are the ones with respect to r and the ones with respect to s. Do y'all see that? Now, to get those two formulas, we have to work with this tree. So I'm going to focus right now on this one. But I'm going to create the tree, the entire tree, the picture for the entire tree. So let's go down this left branch here. Z going down to x, that would be what kind of derivative? Partial. Partial z with respect to x. And then let's go down this right side. Partial z respect to y. How about this x down to the r? It's a partial, right? It's a partial because x depends on two things. Partial x with respect to r, and then partial x with respect to s, partial y with respect to r, partial y with respect to s. Do y'all see that? Everyone make sense out of this? Now, if two of them are possible, two derivatives ultimately are possible, this first one can't just be all the branches, can it? Because then the next one would be identical, right? So the way we're going to get this one is to only go down the branches that lead us to what? To r. So to do this yellow one, I want to start at z and look down and say, does this path down here, does this lead me to r? Yes, I've got to go down here. That gets me to x, and then down here it leads me to r, but I don't go down this way. And then the other side, I come down and then come down. Multiply and add, correct. Down the branches you multiply. When you have multiple branches, you add. So what we would have here is that the partial of z with respect to r would be partial z with respect to x times partial x with respect to r plus partial z with respect to y times partial y with respect to r. Do y'all see that? Coming down this branch, those two multiplied, plus down this branch, those two multiplied. That's your partial derivative. And then we could do the same thing for the other one, right? But now we would go down, start at z, we'd come down and over, and then over here we come down and go this way, and that would be this one. I'm going to stop class. Y'all okay with that? All right. I'm having like major heartburn right now. I don't know what's happening. Falling apart, man. God dang. But we've also gone pretty far past what we were supposed to go today. I don't want to get too far ahead of ourselves. On your take-home, you can actually do number 1 completely right now. This will be due, let's see, we'll shoot for next Wednesday, but I don't think so. How about the Monday after that? Is that when our test is? Crap, man. Today's 24. Let's make this due on the 6th. October 6th. All right, we'll call it a day. Y'all have a good rest of your day and rest of your week, rest of your weekend. Remember, if you're going to turn in that assignment late, just get it to my office by Friday, 2 o'clock p.m. It's not late if you're going to turn it in. You won't be penalized.